Get ready to uncover the invisible engine powering circuits, sparks, and the structure of matter itself. How do electrical systems actually do work and store energy? In this video, we'll uncover how electric potential shapes the motion of charges and how electric energy is quietly packed into space. This is electric energy. As a little bit of review, work is ultimately a transformation of energy, and the work done by conservative forces is path independent. That means that it doesn't really matter which type of path we take to move an object with a conservative force. We only need to consider its initial and final states to say something about the energy change in that motion. The work is equal to the force vector dotted with a distance vector. If we multiply this out, we can see that the work is equal to force times distance over which the force acts times the cosine of the angle between the force and the distance. As a reminder, work has the SI unit of joules, which is also equal to a Newton times a meter, and work will be positive if the force is acting in the same direction as the displacement of the object, whereas work will be negative if the force is acting in the opposite direction of the displacement. The work done by a conservative force will always be equal to the negative change in potential energy of the system. And some conservative forces that we've seen in the past would be like the spring force, the gravitational force, or now our electrostatic force. Since electric fields are capable of exerting forces over a distance, they can do work on charged objects. And if we use what we know about the electric force in this work equation, we can say something about how much work would be done to move a charge, some displacement, using an electric force. The work done on a positive charge would be positive as it moves from this left side of this electric field to the right side of this electric field. As a positive charge moves with the electric field, positive work would be done on that charge. In other words, a force acts over a distance to cause this charge to accelerate. It's going to gain kinetic energy as it's repelled from this positive plate and pushed to the right. That force will cause for that charge to gain some velocity, and ultimately this kinetic energy that was gained for this charge was gained from the electric field acting on it. And so there's a new kind of potential energy that we need to consider that was transformed to create this kinetic energy. This is the electric potential energy. This is entirely consistent with our understanding of the gravitational potential energy, where if gravity is acting to pull some mass down a hill, initially, the mass had some gravitational potential energy stored, and as it gave up that gravitational potential energy, it gained kinetic energy. The same type of situation applies to a positive charge being affected by an electric field. Specifically, the electric potential energy is the energy associated with a charged particle based on its position in an electric field. Of course, the energy still has the SI unit of joules, and as with any potential energy, we will always measure the change in potential energy with respect to some reference point. That means usually it's more useful to set a reference point and determine how much the potential energy changed by comparing to that reference point, rather than just arbitrarily saying that a system has some amount of potential energy. This is all based on a reference point, so it's not like the potential energy as an absolute value is all that relevant. Really what matters is how much the potential energy changes by. And this change in potential energy is ultimately manifested in a work that would be done by an electric field. An electric field causes a positive charge to feel forced in the direction of the electric field, and so electric potential energy would be removed from that charge field system, and that change in electric potential energy would be based on the work done using the force of electricity times the distance over which it acts. This is specifically talking about the work done by the electric field, not by some external agent that would have to grab onto this particle and pull it up the electric field. Instead, the electric field itself does work on the charge to cause it to accelerate. A positive work means that the charge is losing potential energy and gaining kinetic energy, and a negative work means that the electric field is causing for the charge to gain potential energy and lose kinetic energy. This is sort of like trying to have gravity cause for a ball to roll down a hill, or gravity slowing down a ball as it rolls up a hill. Essentially, the gravitational field would act on that mass, pulling it down the hill, causing it to lose potential energy and gain kinetic energy. And the opposite would be true if we tried to roll a mass up a hill. Gravity would slow that mass down as it's trying to roll up a hill, causing it to lose kinetic energy and gain gravitational potential energy. In this way, moving a mass through a gravitational field G is a lot like moving a positive charge through an electric field E. The gravitational field does positive work on the mass as it goes down in the gravitational field, and so this mass would accelerate. It would gain kinetic energy based on the work done by gravity, and that kinetic energy would be equal to however much gravitational potential energy was lost in that process. In this case, the system must include the gravitational field of Earth and the mass of the object to think about energy being conserved throughout that system. On the other hand, the electric field would do positive work on a positive charge as it moves through the electric field. This would cause it to decrease its electric potential energy and gain kinetic energy. We would see that the work done by the electric field leads to an increase in the kinetic energy or a decrease in the change of the potential energy. And in this case, our system would be the charge and the electric field. Now, one thing that's different between the gravitational case and the electric case is that we can have a negative charge. And so if we are talking about a negative charge moving through an electric field, the signs essentially are the opposite for a negative charge. We would see that the system would gain potential energy as we move with the electric field for a negative charge, and it would lose kinetic energy as it goes against that field. So in any case where we have a charge present in an electric field, we would have an electric potential energy. This means that between 2 point charges, there will be an energy associated with those two charges being near each other. If I have a positive charge and I put it close to another positive charge, those charges will want to repel from each other. There's energy stored up as I try to push those positive charges together. It's potential energy, it's stored. And if I let go of those charges, the potential energy would be transformed into kinetic energy, causing the two particles to accelerate outward, decreasing the system's electric potential energy and increasing the kinetic energy of each particle. The work done to push 2 point charges together or to put them in a certain configuration near each other could be calculated and ultimately is a measure of the potential energy of the system. So the potential energy between 2 point charges will depend on Coulomb's constant, the value of the first point charge, the charge value of the second point charge divided by their distance separating them. The potential energy is a scalar just like all other energies, but it can still have a positive or negative sign depending on where you set your reference point for the potential energy. If we have a negative potential energy, that implies that the particles are being attracted. That would be what we get if we put a negative and a positive in for this equation. So remember that you do have to include the signs for Q1 and Q2. A negative and a positive would be attracted. You'd get a negative potential energy there. On the other hand, if we have two like charges, they would be repelled from each other, and that system would have positive potential energy stored up in it. As the two particles get farther and farther away from each other, eventually they'll be so far away from each other that this potential energy term will essentially equal zero. That's when the particles are infinitely far away from each other, the potential energy of the system would be zero. The graphs on the right here show the case where if we had a positive charge and we were trying to bring a negative charge near that, the farther away that negative charge is, the lower the value of the potential energy would be, but it would still be negative. So we see that as we get closer, as the two particles get closer, the potential energy becomes much greater in the negative direction until eventually when they're right on top of each other, the potential energies of the system would be essentially infinity. On the other hand, if we had two positive charges that were repelling from each other, the The farther away that they get, the lower their potential energy is of that system, and the closer together they are, the higher the potential energy would be. This can ultimately be used to determine the energy associated with bonding two ions together. If we have an ionic bond with a positive and a negative ion, like sodium plus and chlorine minus, those two ions will be attracted to each other due to electrostatic attraction. And you can see the shape of this attraction curve showing up when the particles are at a certain distance away from each other. This inverse 1/r type of shape here, as the particles get farther and farther apart, ultimately tells you how much energy is associated with their attraction. The closer together that the particles become, eventually the other types of interactions take hold and dictate the energy of that system. So if I have charges present in an electric field, there will be some potential energy stored up between those charges in that electric field. This still applies in the case for an electric dipole, where I have two equal charges separated by a small distance d. In this case, we could calculate the potential energy of a dipole system based on its alignment with an external electric field. A dipole would rotate with a field due to a torque, as we've seen previously. Depending on how aligned that dipole is with the field, if it's perfectly aligned, it would not feel any torque, and therefore it would not have any potential energy associated with it. But if I was to grab onto that dipole and torque it and put it at an angle with respect to that electric field, now the dipole wants to align with the field. It's got energy stored up, and the second that I let it go, the dipole will try to align with the electric field. In other words, based on the alignment of the dipole with the field, we could calculate an electric potential energy of a dipole in that field. And the equation is ultimately a dot product between the electric dipole moment and the external electric field. How that looks is negative the dipole moment times the electric field strength times cosine of the angle between those two vectors. An aligned dipole would be at a minimum potential energy, whereas an anti-aligned dipole would be at a maximum potential energy. The electric potential, V, is a very difficult idea to wrap your head around, but follow me on this one. Essentially, the electric potential is a measure of how much energy is stored based on the amount of charge in a system at some particular point in space. It's like a map of how the energy looks for a certain amount of charge at some point in space. We'll continue looking through this, but let's continue. The unit for the electric potential is volts, and it also has the letter capital V. So you read that right. The variable is capital V for electric potential, and its units is volts, also a capital V. Many times your instructional team in the textbook will refer to the electric potential V as just potential. But potential is different than potential energy. These two are not the same thing. These two measure completely different variables in completely different units. The electric potential energy is U subscript E, and it's measured in joules. The potential is V, and it's measured in volts. So essentially the equation, the general equation for the electric potential, is the amount of energy in a system divided by the amount of charge in that system. The potential essentially says the way that a positive charge would be forced based on some other electric field, based on being present in some electric field. So if I took a positive charge and I put it near another positive charge, this positive charge would feel forced away from the other positive charge. It would go with the electric field, and it would go down in electric potential. The electric potential is very high for positive charges right on top of them, and as we get farther away, the electric potential decreases. The same type of thing is true for the electric potential of a negative charge, except a negative charge has a negative electric potential. And so the closer that a positive charge gets to that negative charge, the greater the force that it would feel, the more energy that it would have stored up, and ultimately a positive charge would roll down this electric potential hill. It would feel forced with the electric field toward the negative charge, and it would go down in potential. We again revisit the idea of our electrical hill. This is an excellent analogy to help you understand how the electric force, electric field, and electric potential all interact together. If we think about gravity, the gravitational field is like a field that pulls objects down in that field. And we could say that the gravitational potential of a system is based on how high the particle is on that hill times the strength of the field. So for a given mass, the gravitational field can only do so much work on a mass based on how high up it is on a hill. Once the mass rolls all the way down the hill, there is no more energy that could be imparted from gravity onto the mass. In other words, once it rolls down the hill, there is no more gravitational potential for this system. It has no more energy that could be imparted by strictly gravity. This is the gravitational potential, not the gravitational potential energy. In a similar type of sense, the electric potential is sort of like a measure of the height of our electrical hill. For a given charge, the electric field can only do so much work on a charge, and this is called the electric potential. If I had a positive charge in this electric field, it could go with that field to a different point until there's no more field for it to travel across. And this is essentially a measure of the electric potential. It is the amount of energy contained in the system per unit charge. Electric potential can come about from a single point charge. A single point charge creates an electric field everywhere around it that would force any other positive charge one way or the other. And this electric field is essentially telling you something about the potential landscape around that point charge. We can calculate the potential from a point charge by using this equation here, where we see the Coulomb constant K times the charge of our source generating that electric potential divided by the distance to some point of interest. Here, R is a distance measured in meters, and capital Q is the source charge that generates an electric potential. It's the same type of idea as the source charge that generates an electric field. And now we see that if we're directly on top of a charge, if we're right on top of this positive charge over here, our R would essentially go to 0 and our electric potential would go to infinity. However, as we get farther away, our electric potential decreases, and it's sort of in an inverse distance type of relationship. So the electric potential decreases as we get farther away from that positive charge. Keep in mind that you need to include the sign of capital Q here. A negative charge generates a negative potential. So the closer that I am to this negative charge, if my R equals 0, my electric potential essentially goes toward negative infinity as I get closer and closer. And if I get farther away from that negative charge, the electric potential would be a lower negative value at that point in space. The electric potential is a scalar, which means that it can be positive or negative. That would depend on if a charge was positive or negative generating that potential. But the total electric potential at some point of interest, P, would be the addition of all of the electric potential contributions from each charge in the vicinity. The separate potentials would add together in a scalar addition type of sense. We don't need to worry about their direction, just their value, whether it's positive or negative. So this first charge would generate a potential landscape around it that would dictate something about the electric potential at this point. The second charge would generate its own electric potential landscape, and at that point we would add that electric potential some distance away, and the third charge would also generate its own electric potential landscape, and we could add that, thinking about the sign of each of these, and that would be used to calculate the total electric potential at some point in space. Potential is always measured in comparison to some reference point that we set. In other words, a strict measurement of potential at one point is based on wherever we put our reference point. Really, what is more useful is the potential difference between 2 points. if we think about how much the electric potential would change between these 2 points, we can say something about how the energy per unit charge changes when I move from one point to another. The electric potential difference is also called the voltage. So very commonly, you'll see that the voltage is equal to delta V, the difference between 2 points. Maybe that's like a voltage potential final minus a potential initial, or potentially just a potential at some point A minus the potential at some point B. In this way, the potential difference is a relative measurement of how much the energy would change in a system given the amount of charge in that system. So if I know how much my electric potential changes by when I move some charge through a field, and I know what the value of that charge is, I can calculate the change in the system's potential energy, delta UE. Again, make sure that you include the sign of Q in this equation. It is not an absolute value, so the change in potential energy will depend on what kind of particle is moving through our potential landscape. If we have a positive charge, positive charges spontaneously want to go from high potential to low potential. A positive charge is like a mass rolling down an electrical hill. But a negative charge, on the other hand, spontaneously will try to move from low potential to high potential. It moves in the opposite way as a positive charge, which is a little bit tricky to think about. So again, a positive charge spontaneously wants to move from high potential to low potential with the electric field, and a negative charge wants to spontaneously move from low potential to high potential against an electric field. This gives rise to a new unit for energy called the electron volt. This is essentially the amount of energy required to move one electron across a potential difference of 1 volt. So if I take the charge of an electron and 1 volt and multiply them together, I essentially get a measurement of the amount of energy for 1 electron volt. And 1 EV is said to be equal to 1.6 times 10 to the 19 joules. The electric field and the potential are very closely related to each other. Essentially, the electric field is a measure of the slope or the rate of change of the potential with respect to position. One way of writing this out is to say that the potential difference between 2 points is the electric field times the distance between those 2 points with a negative in there. This distance can be along any path. It could be a delta X, it could be a delta Y like you see in the diagram over here. It could be a delta Z, or it could be a diagonal type of path. In this way, we see that the electric field is actually based on a potential difference over some distance. So we previously labeled the electric field as having units of newtons per coulomb. But if we think about the units from this equation in the box, we see that an electric field also has the units of volt per meter. These are the same unit. They're equivalent to each other. So a volt per meter is equal to a newton per coulomb. And remember, we need to measure the potential difference with respect to some reference point. So usually it will be very convenient to set the negative plate of a parallel plate conducting system as V equals 0, so that we have a positive voltage up near the positive plate and a voltage of 0 near the negative plate. But again, you can arbitrarily set this reference point to be wherever you want, and what really matters is the difference in potential between the positive plate and the negative plate. In this way, we see that if the electric field points from positive charges to negative charges, the electric potential will have a high potential at positive charges and a low potential at negative charges. Really, the electric field is essentially a measure of the slope of the electric potential with respect to position. If my electric potential is changing a lot with respect to position, if I have a very steep slope, that implies that I have a very strong electric field in that direction. However, if my potential is changing with a very shallow slope, it's not changing very much with respect to position, then that would imply that I have a weak electric field. And this electric field can be done for any direction. It can be done in the direction of X, where we would plug in delta X for our distance between 2 points, but this could be done for 3 dimensions as well, thinking about a delta X, delta Y, and delta Z. We will now merge our understanding of the electric potential with the electric field by drawing equipotential lines. These are imaginary lines that are used to map out the electric potential landscape around some charged object. This is essentially like a contour map that measures the height of our electrical landscape. It measures the potential at different points. And each of these equipotential lines in green represent a value where the potential is equal everywhere along that line. So right at this line, we could say something like our potential equals 1 volt. But then as we step closer to that positive charge, our potential would go up. So our potential might be 2 volts as we step closer, and then 3 volts. These are just arbitrary values, but we can calculate this based on our electric potential of a point charge to figure out what these exact values would be some distance away from that point charge. Here's an example of an equipotential map with specific values included. Here you'll see that I have a positive 1 nanocoulomb charge at the center of the diagram here. This is a point charge, and we see that the electric field points outward. That's these white arrows, points outward from the positive charge everywhere throughout space. This is a vector map of the electric field, and as we get farther away, these arrows are weaker. They're more transparent, indicating that the electric field gets weaker as we get farther away from that positive charge. But if we were to use the equipotential lines to map where the potential is equal at various points around that positive charge, that electrical landscape could be mapped with these equipotential lines. Here we see that our potential is 5 volts, but as we step closer, we increase our potential to higher and higher values until eventually the potential spikes up to infinity as we get closer and closer to that positive point charge. Equipotential lines can also be drawn for a system of multiple charges. In the case of a dipole, where we have a positive and a negative charge, we could think about how the electric field would look around those charges. And we know that the electric field would point from the positive charge toward the negative charge, outward from positive in every direction, and inward toward the negative from every direction. And these electric field lines can never cross each other or form a closed loop. What we see is that the equipotential lines in green are always perpendicular to the electric field lines, and we would have high electric potential near this positive charge and low electric potential near this negative charge. It's like on the right side, we have an electrical mountain that dictates the potential landscape near the positive charge, and near the negative charge, as we get closer to the left side, we have an electrical sinkhole. This dictates how a positive charge would move around that electrical landscape. If I started with a positive charge near this other positive charge, if this was a positive Q right here, it would want to roll down that electrical mountain into that electrical sinkhole. It would move from positive high potential to low potential. Here's a map of the electrical landscape around a dipole consisting of a positive and a negative charge. Remember, we can set our reference point to be 0 anywhere we want. Sometimes it will be more convenient to set our reference point to 0 directly on top of the negative charge. But in this case, since that electric potential approaches infinity as we get closer, maybe it would be more convenient to set our electric potential as 0 right between these two charges. In this way, we see the electric field points from the positive charge to the negative charge. The equipotential lines are always perpendicular to that electric field throughout space. And we have positive electric potential as we approach closer to the positive charge, increasing as we get closer. And we have negative electric potential as we get closer toward that negative charge, getting greater and greater in the negative direction. And here's another map of the electric dipole using continuous electric field lines. You can see that the equipotential lines in red and blue sort of look like contours that tell you where we're at higher electric potential and lower electric potential. That'll dictate the way that a positive or negative charge would move in that electric field when it's present in that electric potential landscape. For two like charges, the electric field and equipotential lines are a little bit more difficult to draw, but we've seen this previously. If we have two like charges like this negative and negative charge, the electric field would go inward toward both of those negative charges everywhere throughout space, and we would see that the electric field would be 0 right in between those two like charges. When we map our equipotential landscape around these charges through this electric field, we see the equipotential lines are always perpendicular to the electric field, and they get greater in the negative direction as we get closer toward a negative charge, and they increase in potential as we get farther away from those sources that are generating that negative potential. So over here we have increasing potential. The delta V would be increasing as we move farther away from those negative charges. If we were to map the exact equipotential landscape of two like charges, here we have two positive charges, each at 1 nanocoulomb, and we would see that we can once again arbitrarily set our reference point to be 0 wherever we want. In this case, we have set V equals 0 at a value of R equal to infinity. As I get farther and farther away from these positive charges, my potential goes down. We can pick a convenient point to call 0, and that would be when we're infinitely far away from this system of charges. If I were to put my reference point in the middle like we did previously, we would see that the electric potential would be negative as we get farther and farther away. So that wouldn't be very convenient. Instead, in this case, we're just going to map the electric potential with infinitely far away being 0, and we see that the electric potential increases as we get closer to each of these positive charges. And in this case, they're perfectly symmetrical based on how they're spaced apart. So here is your summary of all of the point charge equations for electrostatics. There's definitely a lot to keep track of, and the equations are very similar to each other, so please pay careful attention. The electric force is always a vector, and you must have two charged objects in order to have an electric force. On the other hand, an electric field is also a vector, but it can be generated just by one source charge off on its own. The electric potential energy requires two charged objects to be in the vicinity of each other to store up energy. And the electric potential could be generated just by a single point charge off on its own, and that would dictate the electric potential landscape around that source charge. And here's our summary of electric field lines and equipotential lines. You will see that electric field lines always point outward from positive charges and inward toward negative charges. They can never cross each other, and the closer together they are, the greater the electric field strength is. On the other hand, equipotential lines will always be perpendicular to the electric field lines, and the electric potential is like a measurement of the height of our electric hill. It tells us how much energy could possibly be extracted per unit charge given some system in a certain configuration. Now that we've spoken about the electric potential energy between two charged objects, we can revisit our idea about energy conservation. Energy conservation still holds true even for electrical systems. So if I have an isolated system, the total amount of energy in the beginning of some process will be equal to the total amount of energy in the end of that process. That involves thinking about the potential energy and the kinetic energy and how it changes between an initial and a final situation. Now, though, we have a measure of the potential energy, the electric potential energy. And so, however much kinetic energy was gained by some system is equal to negative the change in the potential energy. And if we have a equation for our electric potential energy, we can now calculate how much kinetic energy would be gained for moving some charge through a potential difference delta V. Notice that in this equation, Q is still not absolute valued, so the sign of this charge matters, and that means that if I'm moving from high potential to low potential, if I have high V to low V, like you see in this diagram here, for a positive charge, my delta V would be V final minus V initial. My initial number was higher than my final, so my delta V would end up being a negative value in the case that we're seeing here, and that means that a positive charge would gain positive kinetic energy in this case when it moves from high potential to low potential. The capacitance of a system essentially dictates the amount of charge that could be stored for a given potential difference. If I apply a voltage to some system, we're capable of collecting charges in that system in such a way that stores up energy. And the more voltage that is applied to that system, the more charge could be stored. So The capacitance is ultimately the amount of charge stored in a system divided by the potential difference applied to that system. Capacitance has a new unit called farads, which has the letter F, and it is essentially a coulomb divided by a volt. A capacitor is a system that's capable of storing up energy in the electric field between two conductors that are oppositely charged. And if you've ever seen the insides of a computer or some type of complex circuit, you would see little electrical devices that look like what you see here. These are capacitors. They store up charge temporarily for a system. The simplest type of capacitor that we can have is called a parallel plate capacitor, which you've actually seen quite a bit already up to this point. A parallel plate capacitor is two conducting plates that are oppositely charged, parallel with each other, and they are the same size on both sides. Both those plates are symmetrical. So this is an example of a parallel plate capacitor that is capable of storing some amount of charge given the potential difference, however much voltage I apply to that system. Essentially, the capacitance is a number that tells you how much charge could be stored for a given potential difference. A voltage or a potential difference could be applied by something like a battery. It supplies 10 volts to the parallel plate capacitor, and given that voltage, we will be able to stuff a certain amount of charges onto each of those plates. And if I attach another battery that's bigger, I'll be able to store more charge onto those two plates. But ultimately, the ratio of how much charge I can store to the potential that's applied is a measure of the capacitance of the system. This capacitance for a parallel plate capacitor is precisely a result of the geometry of the capacitor. Essentially, the capacitance depends on the permittivity of free space, the area of the plates, and the distance that separates those plates. So if I have a larger area for my parallel plate capacitors, I'm capable of storing more charge on them. However, if my plates are farther apart, the attraction between the positive and negative plates isn't as strong. It's harder to stuff electrons or charges onto those parallel plates. So the capacitance decreases as the distance between the plates increases. The permittivity of free space is essentially a constant of our universe and will always adopt this value, and the units are in farads per meter. Briefly, I'd just like to mention that we can have other types of capacitors that are not just two square parallel plates. That's the simplest type of geometry that we could have, but there's many other more complicated geometries like a spherical capacitor that has one conducting sphere on the inside that might be positively charged and one conducting sphere on the outside that might be negatively charged. This is essentially the principle that is at work behind a Van de Graaff generator. And while these systems are possible to have in reality, generally such a system would be outside of the scope of a pre-med physics class. The capacitance also needs to have one other thing other than two parallel plates that are both conducting. A capacitor needs to have a dielectric between those two plates. There needs to be a resistive medium that prevents charges from hopping from one plate to the other. If these two plates were connected by a piece of metal or some type of wire, all the positive charges would just go along that wire toward the negative charges and the system would neutralize. Instead, we need to make sure that these two plates are separated by a resistive medium called a dielectric, which prevents those charges from hopping from one plate to the other. And the dielectric medium, the material between these two plates, will always have a dielectric constant associated with it that tells you about its dielectric strength. Basically, how strong of a dielectric is a material, that will dictate how difficult it is for charges to move through that material and will essentially have an impact on the capacitance of a capacitor. Real quickly, I'd like to note that the dielectric constant is a unitless quantity, and so the dielectric constant for a vacuum is given as just 1, but other materials will have differing dielectric constants, essentially dependent on how resistive or insulating they are. This gives rise to the permittivity of a medium. The permittivity is essentially a measure of how easily an electric field can permeate through a region of space. How much does a certain material permit an electric field to pass through it before that electric field dies off? The permittivity is measured in farads per meter, and the permittivity of free space is called epsilon 0. That value was given in the previous slide. It's a constant for our universe. And the permittivity of some dielectric material will always be the dielectric strength times the permittivity of free space. The permittivity essentially tells you how much a dielectric medium will be polarized when an electric field is trying to pass through it. The electric field will die off more in a system that has a greater permittivity and a greater dielectric strength. So the electric field within a dielectric material can be calculated by taking the electric field in a vacuum divided by the dielectric strength of that material. So technically the capacitance that you saw in the previous slide, that equation was relevant to a capacitor that had a vacuum as its dielectric medium in between the two plates. But in reality, we will usually have a material in between those two plates, something like paper or plastic or wood or something like that, separating these two conducting plates. And that dielectric has to be insulating so that the charges can't hop between the plates. And now the capacitance of a parallel plate capacitor is modulated by the dielectric strength of the medium between the two plates. So the official capacitance equation is the one in the box here, where previously kappa just equaled 1 for a vacuum. If we were to simplify this, we can essentially take the capacitance of a capacitor in vacuum multiplied by the dielectric strength of a dielectric that is placed between the two plates, and that would tell you about the new capacitance with that dielectric between the plates. So as we attach a battery to a parallel plate capacitor, we establish a potential difference or a voltage that forces charges to be collected on the plates. In other words, we did work to move charges onto that capacitor and store them there. We did work to move those charges there, and if I remove that battery and hook that capacitor up to a light bulb or something like that, the charges can flood out of the capacitor into the light bulb. This means that we did work to store the charges on the capacitor, and a charged capacitor would have an electric potential energy U in that case. If we had an uncharged capacitor, it would initially have 0 charge on it, and that would happen if we applied 0 voltage. But as we increase the voltage that is applied to that capacitor, we would also increase the amount of charge stored. And the area under this relationship can tell you about the amount of energy stored in the capacitor. Essentially, the energy stored in a capacitor can be calculated based on the charge stored on that capacitor for some potential difference that's applied. But using what we know about the general equation for the capacitance, that's this one that you see in the top right, we could rework which variable is in this potential energy of a capacitor. If we wanted to remove the voltage term, we could use that capacitance equation and substitute to say that the energy stored in a capacitor is equal to 1/2 Q squared over the capacitance C. And in a similar sense, we could also say the energy stored in a capacitor would be 1/2 the capacitance times the potential difference that's applied squared. You can use any of these equations to determine the potential energy stored on a capacitor, and really which one you choose will depend on which variables you're given. If you know about the charge and the capacitance, you could use the middle one. But if you know about other variables, you might want to use the other equations. And essentially, this energy is stored in the electric field between the two plates. And that electric field has an energy density then within a volume of space between the plates. But ultimately, this equation for the energy stored on a capacitor should be good enough to get you there for now. That'll cover everything for our unit on electric energy and capacitance. There's definitely a lot to keep track of, so I strongly encourage you to write out your own note sheet right now to help you navigate all of these complex ideas, which are especially difficult to visualize. Thanks for paying attention. I'll see you in the next one.